Today we will solve some exercises and we will emphasize the use of the gain and resistance calculation sheets. So we'll try to solve the exercises using formulas from those sheets. These are exercises from a previous midterm. So let's start with the first one, which you can see. This is a common source amplifier that's loaded by a PMOS current source with a source resistor RS. The inclusion of RS must raise the output resistance of the PMOS current source to 10 times ROM. Assume that the MOSFETs are biased at 0.5 milli, PB is a DC source, and the MOSFET parameters are given. So one thing that we will do, and this is stated on the first page of this exam, is that we will neglect VA or lambda in the DC analysis. So let's start. And I'll copy the circuit here. I have the supply, which is no signal. The resistor RS, I need to find the value of this RS. A PMOS with its gate at some DC voltage, so no signal here, no signal here. This is the supply. And there's an ROP arrow looking up. And a MOSFET, MN, MP, V and V out. So let's verify that this, in fact, is a common source amplifier. The input is here. So this is the gate of MN. The output is here. This is the drain of MN. So this is the amplifying MOSFET with input at gate, output at drain, and the source is grounded. Okay, so gate, drain, source, and in fact, we can consider this to be a common source. But what's between the drain and the supply and signal ground is interesting. I have another MOSFET and a resistor, and this other MOSFET and the resistor RS, they're acting as if maybe this is some kind of current mirror, some kind of current source. And the resistance seen, looking into them, looking into this here, is called ROP. And I want to find RS to get a certain ROP. Okay, so this MOSFET MP has no signal at gate. And I am looking here into its drain. This is the drain of MP, and this is the source of MP. So I'm looking into the drain of MP with no signal at gate and a resistor RS between its source terminal and ground. So let me relate then ROP to the parameters of MP and RS. And this is where we will use the resistance formula sheet. I don't need to memorize what is the resistance when I look into the drain of a MOSFET with such conditions. So we go to the resistance formula sheet, which is shown here. And I look for the resistance looking into the drain when there is a resistor from source to ground. So this is the formula But the formula shows an N MOSFET, and that's perfectly fine. It doesn't have to be N MOSFET to apply the formula. It can be N or P, the same formula would apply. So if I'm looking into the drain of a MOSFET with no signal at gate, that's what's shown on the number 6 in the formula sheet, no signal at gate, and the small resistor RS between the source terminal and ground, the resistance would be small RO of the MOSFET plus small RS plus GM RORS. So looking at my problem at the exercise, I'm looking into the drain of MP with big RS between its source terminal and signal ground, and therefore ROP would be given by the formula small ROP plus big RS in this case plus GMP ROP RS. So this is ROP, the resistance seen looking into the drain of MP. So now this ROP is like RD for MN. So this is V in, V out, and ROP. Effectively, this is what's happening. It's like ROP is an RD for MN. All right, so let me go back to the given and see. The given stated that ROP should be 10 times RON. So this ROP should be 10 times RON of MN. And I need to solve this to find the RS. Okay, so RS is the unknown. Hopefully I can find RON and ROP and GMP. Well, if I neglect VA in the DC analysis, then ROP would be VAP over IDP. This is, I can use this when I neglect lambda or VA and DC analysis only. And RON would be VAN over IDN. Now IDN is equal to IDP. This is the only current that flows in the circuit here. This is the current flowing in MP and MN. It's the same current. IDN is equal to IDP is equal to 0.5 milli. That's in the given. So IDN and IDP are known. 0.5 milliamp. VAN and VAP are not given, but I have lambda N and lambda P. Lambda N is 0.1 per volt and lambda P is 0.1. So VAP must be 10 and VAN must be 10. And therefore ROP is equal to RON, and that's 20 kilo ohms. Okay, this means that big ROP should be 200 kilo ohms, 10 times RON. Okay, we're well on our way. We still need GMP. GMP is IDP over half VOV, so 2 ID over VOV of P, and ID is 0.5 milli. That's easy. I need VOV for the P MOSFET. What is VOV for MP? I can easily find it. So from the current equation in SAT, and I said that we will neglect VA, so ID is half K prime PW over L of the P MOSFET times VOVP squared. So let me use absolute value for P MOSFETs. I don't have W over LP. Let me scroll down. It's okay. So the question is find RS if W over LP is 150. Actually, I know what this is. So this is 150. That's W over L for MP. K prime P is given 0.1 milli. ID is given, so I can find VOVP. So VOVP is 2 times 0.5 milli, right? VOVP squared is 2 times ID divided by K prime P, 0.1 milli times 150. And this will give me a VOVP value of how much? 2 times 0.5 over 0.1 times 150, square root of that. And I get 0.258 volt. So that's VOV, and now we can find GM. 2 times 0.5 milli over 0.258. That's 3.876 milliamp per volt. All right. That's GMP. All right, I think we have everything. So now I need to solve 200K. That's our big ROP, 10 RON. 200K is 20K plus the unknown RS plus 20 times 3.876 RS. Okay, now that's an easy equation to solve, and we can get the value of RS. 2.29 kilo ohms. All right. So a 2.29 kilo ohm resistor inserted between the source terminal and no signal would increase the resistance that we see from 20 to 200. We add a 2K resistor, and the resistance seen looking into the drain of the P MOSFET would increase from 20 to 200. That's a pretty good deal. And that's the value of RS that we will need to get this. And let's verify. In fact, it's 2.29 kilo ohms. Determine the value of W over Ln to obtain a gain, a voltage gain of minus 30. So now we're given that V out over V in is minus 30, and we need to find W over Ln. So what is W over L for the N MOSFET? Okay, we established that this is a simple common source amplifier, even though it has 2 MOSFETs and a resistor. It's really just a simple common source amplifier. And we will go now to the formula sheet for gain, the gain formula sheet to find the gain for a common source amplifier. So this is the gain formula sheet, and the common source amplifier is on the first page. So common source, whether NMOS or PMOS, if RS is 0, yeah, there's no RS here. The RS in this circuit is not the same as the RS in the formula sheet. The RS in the circuit is used by the P MOSFET, and we're inserting it to make the resistance ROP large. The RS in the formula is the resistance between the source of MN, the amplifying transistor, and there is no RS between the source terminal of MN and ground. So RS is 0. So if RS is 0, I get this formula. AV is minus GM times RO parallel RD. All right, so this is the gain minus GM of the amplifying MOSFET, so minus GMN RON parallel RD. What's RD in my circuit here? It's ROP, big ROP. This is the RD that we use in the formula from the formula sheet. So I have RON 20K, I have ROP 200K. The gain should be minus 30. And this means that I can determine GMN. So GM is therefore 30 divided by 20K in parallel with 200K. So that's the value of GMN, around 1.65 milliamp per volt. So that's GMN. Can I find W over L from GM? Well, I know ID. I know GM. I can find VOV. And if I know ID and VOV, I can find W over L. So let's find VOV. GM is 2ID over VOV. So 2ID, and there's only one ID in the circuit. I don't need to say 2IDN over VOVN. And this means that I can find VOVN. And that's 2 times 0.5 milli over 1.65 milli. So that's 0.606 volt. So now I have VOV and I know ID. I will reuse this formula. ID is half K prime N W over L N VOV N squared. Of course, all these MOSFETs should be in SAT for this to make any sense. And this will give me W over Ln. So 2ID, 2 times 0.5 milli over K prime N is given in the question here. 0.2 milli. 0.2 milli and VOV N squared times 0.606 squared. And this is 13.6 with no units. This is W over L. This is a ratio of W and L. So 13.6. That's W over Ln. Yeah. The third question is about output voltage swing, and it doesn't require, we will not solve it because it doesn't use the formula sheets. We will move to another exercise that makes use of the formula sheet. So let's try this one. That's interesting. Find the voltage gain V out over V in of the amplifier shown. Okay, amplifier with 3 MOSFETs. Okay. Why not? What kind of amplifier is this? Where's the input? The input is at the gate of the N MOSFET. The output is where? The output is at the drain of the same N MOSFET. So input at gate, output at drain for this MOSFET. So this must be a common source amplifier. But the source of N, of the N MOSFET, of MN, the source is not grounded. Right? The source here is not at signal ground. So there's something between the source and the ground, which is M1. So it's like a common source with a resistor between source and ground. But it's not a regular resistor, it's a MOSFET. And then we have M2 between the output and the supply, between the drain of MN and the supply. So M2 is like an RD, and M1 is like an RS. So this circuit is, in fact, a common source amplifier that looks like this, except that the resistors are not really simple resistors, they're MOSFETs. So RD and RS are implemented using MOSFETs. And no sig here, no signal. This is the supply. So how is RD and RS implemented as MOSFETs? RD would be the resistance seen looking into the, so RD is really M2. And RD is the resistance seen looking into the drain of M2. This is the drain of M2, this is the gate of M2, and this is the source of M2. And at the gate, there's no sig. And at the source, there's no sig because pure DC sources there, no sig, no sig. And the resistance RD would be whatever I see looking into the drain of M2. What about RS? RS is implemented using M1. So here's M1, another P MOSFET. Again, gate, drain down, and source here. So this is RS. It's the resistance seen looking into the source terminal of M1 with no signal at gate and ground here. So of course, no signal. And that's RS. All right. So the three MOSFETs are, MN is the amplifying MOSFET, and it's a common source configuration with RD and RS implemented by P MOSFETs. RD is the resistance seen looking into the drain of M2, and RS is the resistance seen looking into the source of M1. All right, back to the given. I want to find the voltage gain, and I'm given the values of RO and GM. So the voltage gain for a common source with source resistance with RS between source terminal and ground. Let's go to the gain sheet. Gain sheet, common source with source resistance. If RS is 0, no, with RS, but neglecting RO. With RS, but neglecting RO. I'm given an RO for MN, right? Let's go back, double check. Oh, wait. And the transistor MN has a long channel, i.e. lambda is 0. So only MN has an infinite RO. So only for MN, its RO is infinite because it has a long channel. So lambda is 0. So there's no RO for MN. So when I look for the formula, I will apply the formula when there's no RO. Okay, so it is. This is the formula when there's no RO. Minus GMRD over 1 plus GMRS divided by alpha, but alpha is 1 for a MOSFET. So minus GMRD over 1 plus GM over 1 times RS. So gain is V out over V in is minus GMN, the amplifying MOSFET, RD divided by 1 plus GMN RS. This is the formula when RO is very large. Okay, so this is, I need now to find RD and RS. RD is the resistance seen looking into the drain of a MOSFET, and RS is the resistance seen looking into a source of a MOSFET. So what do? We go to the resistance sheet, and this is the resistance sheet, and I want the formula for, oh, here it is. the resistance seen looking into the drain of a MOSFET when there's no signal at gate and no signal at source. This is the situation for M2. So R is simply small RO, which means that RD is small RO2. That's it. That's RD is small RO2. What about RS? RS is the resistance seen looking into the source terminal of a MOSFET, M1 in this case. So let's look for that. This is looking into the drain, looking into the drain, looking into the source. Oh, here it is. If I'm looking into the source of a MOSFET with no signal at the gate, and the small RD, I don't have a small RD in this case because the drain of M1 is directly connected to ground. So there's no RD, small RD in the formula here. There's a small RD, RD plus RO over 1 plus GM RO. In my situation with M1, I don't have a small RD. Small RD is 0. So what does this mean? It means that RS would be given by the formula 0, no small RD, plus RO of M1 divided by 1 plus GM1 RO1. That's the formula that we get from the formula sheet. Okay, so now I have RD and RS, and let's see. Assume all MOSFETs have the same GM. So GM1 and GMN are equal, and also RO1 and RO2 are equal, and the product RO times GM is 36. So we can simplify this to minus GM RO, all the ROs are equal and all the GMs are equal, divided by 1 plus GM, right? RO over 1 plus GM, RO. And what is this? We're given that the product GM RO is 36. So this is minus 36 over 1 plus 36 divided by 1 plus 36. And that's minus 36 over 1 plus 36 over 37. So almost 2 there. And we get minus 18.2 volt per volt. That's the voltage gain in this case for this amplifier. Let's solve another exercise. Whoa. Okay, big circuit. Not really that big, one MOSFET, but many resistors there and capacitors. And the circuit shown below, the MOSFET has again a long channel, so the small RO is negligible, very large, and is biased such that its transconductance is GM equals 1 milliamp per volt. All right, so for the MOSFET, there's only one M1. For the MOSFET, RO is infinite and GM is 1 milli. Okay. All the resistors are 21K. So all the R's are equal to 21K. And the capacitors are very large. Okay, these are external capacitors and they're very large. They're not the MOSFET internal capacitors, CGS, CGT, and so on. They're external capacitors and they're very large. And this means that at signal frequencies, these will have zero impedance. This is what we mean by large external capacitors. They will have very, very small zero impedance at the signal frequencies. So C, there's two of them, the two C's, the two capacitors, they become short at the signal frequencies. And the first question here is to identify the type of amplifier stage. Okay, well, let's redraw the circuit at the signal frequencies. And at the signal frequencies, the capacitors will become shorts and the supply will become like signal ground. So here I have signal ground, what was VDD becomes signal ground, and then a resistor R, the output. And the MOSFET. Okay. Now notice the gate of the MOSFET is here. This is the gate of the MOSFET. And now there is a capacitor connected to the gate. So the capacitor will ground the gate. This is the capacitor that's now a short circuit. It will not just ground the gate, it will also completely bypass, it will short R. So this resistor in parallel with the capacitor is now shorted and it becomes useless, basically. And the resistor between the gate and the drain of M1, there was a resistor here. This is now between the drain and ground. And the drain is the output. So the resistor between drain and gate, I can show it like this. Because it was connected to the gate and the gate is grounded. And then I have the other resistor here connected like this. And now this is connected to ground because the other capacitor is like a short. So this resistor is ground, connected to ground. And there was a resistor like this, which is now also between the input and ground. And the input goes to the source terminal of the MOSFET. So this is the input. And this is the resistor between the input and ground because the capacitor is a short. So one way to redraw the circuit is as follows. This, I can completely remove it because it's shorted by the capacitor. This is between the input and ground. This is between the output here and ground. But so is this. That's also between the output and ground. And this, it's also between the output and ground. So I have one resistor R between the input and ground, and three resistors in parallel R between the output and ground, and one resistor which can be removed completely because it's shorted by the capacitor. So this is a resistor between the input and ground, this one. And then I have the MOSFET. And there is a ground at the gate. And now I have this resistor between the output and ground, this resistor between the output and ground, and this resistor between the output and ground. So three resistors between the output and ground, R to ground, another R to ground, another R to ground. So R, R, R. A more efficient way is to just combine them, and the three R's in parallel are equivalent to R over 3. 1 over R plus 1 over R plus 1 over R, and then 1 over that. That's R over 3. So yeah, we can replace the three resistors by one resistor. They're in parallel. So we can just say R over 3 And that's our circuit. The input is at the source terminal of the MOSFET. The gate is grounded, and the output is taken from the drain. And the first question is to identify the type of such an amplifier stage. Well, if the input is at the source, the gate is grounded, and the output is taken from the drain, that's a common gate. We call this common gate. So this circuit is a common gate amplifier. All right. Next question. Find the voltage gain, V out over V in. Okay, so I need the voltage gain for a common gate amplifier. All right. Formula sheet for gain. Here it is. I need to go to the common gate. Common gate. Common gate gain. Remember that the MOSFET has a long channel, and therefore its small RO is infinite. So that's it. That's the formula. Very simple. GMRD when small RO goes to infinity. GMRD is the gain. So V out over V in is GM times RD. But my RD is this R over 3. So GM times R over 3. GM R over 3 is the gain. Common gate gain is positive. So plus GM times R over 3. What was the value of GM? It was 1, I think. And R is 21. So this is 1 times 21 over 3. That's 7 volt per volt. So the gain is 7 volt per volt, as you can see here in the answer. Okay, that's pretty straightforward. Let me erase so that we can keep the circuit simple and clean. I don't need this. Okay, so that's my circuit. And the next question is, for this circuit, find the input resistance Ri in kilo ohms, input resistance. So I need, again, to consult the resistance sheet now. What is the input resistance for a common gate amplifier? So this is looking into the source. The input is at the source. Let's see. Oh, here it is. I'm looking into the source of a MOSFET, and there is a resistor, small RD, and then I see RD plus RO over 1 plus GMRO. But for this MOSFET that we have in the exercise, RO is infinite, so I need to actually use the first formula here, the simple one. The resistance is simply 1 over GM. So looking into the source of the MOSFET, I see in this case 1 over GM, since RO goes to infinity. And GM is 1 milli. So 1 over 1 milli equals 1K. Oh, wait, the answer is 21 over 22. What did we do wrong? Oh, did we? Oh, wait, we forgot about R. This is the input resistance here. The formula sheet gives me the resistance seen looking into the source. So this is 1 over Gm, and that's 1K. But R in the input resistance is not this, because there's R also. So Ri would be R in parallel with 1 over Gm. So they're both connected to the input. I see 1 over Gm looking into the source of the MOSFET, and there's also the R in parallel with that. And now we have 21K parallel with 1K. And that's 21 times 1 over 21 plus 1. So 21 over 22. Okay, that's the right answer. 21 over 22. Pretty close to 1. Okay, here's the BJT example. Exercise the BJT now. Two of them. Calculate the input resistance of the circuit shown. The BJTs are biased at a collector current of 1 milli, have beta equals 100 and VA 50. RC is 12 and RE is 0.6. And I want to find the input resistance of a BJT. So Q1 is has the input at its base, right? This is the input at the base of Q1. And there's nothing between the collector of Q1 and the supply. So signal ground, no sig. A no sig node at the collector. And then between the emitter of Q1, at the emitter of Q1, I have an RE. And I have Q2. All right, I want the resistance seen here. That's the input resistance. Find the input resistance, this. So that's the resistance seen looking into the base of a BJT. So we go to the resistance formula sheet. And let's find the resistance seen looking into the base of a BJT. Here's 1. Number 9, the resistance seen looking into the base of a BJT with no signal at emitter. But no, that doesn't apply here, because for Q1, I have stuff at the emitter. I have RE and Q2. No, next. Or maybe this one. Yeah, so when there's a small RS between the emitter and no signal, then I can use these formulas. Now these formulas, this is a scary formula when there is early effect. But do I have a small RC here? There's no small RC because the collector of Q1 is shorted to no sig. So in the formula, the RC would be set to 0. Okay, and if I set RC to 0, then the formula becomes R, copying from the formula sheet, R pi plus beta plus 1 RS, RO plus 0, so RO over RO plus 0 plus RS. Now, if you look at this quantity, this is RO RS over RO plus RS, so that's RO parallel RS. So R pi plus beta plus 1 small RO parallel small RS. So R pi in this case is R pi 1, beta is beta 1, RO is RO 1. Small RS is what? In the formula sheet, small rs is whatever appears between the emitter of Q and no signal. So what do I have here between the emitter of Q1 and no signal? I have RE and whatever I see looking into the base of Q2, and they're in parallel. So RS is RE plus whatever I see looking into the base of Q1. Again, looking at the formula sheet, when you're looking into the base of a Q of a BJT1 with nothing at the emitter, it's simply R pi 2. Let me fix this. These are not in series. So RE in parallel with R pi 2. When you look into the base of Q2 with nothing between its emitter and signal ground, it's just an R pi and R pi 2 for Q2. So that's a small RS, and the input resistance is therefore R pi 1 plus beta 1 plus 1 RO1 in parallel with RE and parallel with R pi 2. So that's the input resistance. Now, in the given, there are several quantities that we don't know, but we can easily find. So R pi 1, I have IC. It's given IC is 1 milli. So I can find GM1, IC over VT, so 1 over 25. That's 40 milliamp per volt. And R pi 1 would be beta over GM. Beta is given 100. So 2.5 K. VA is 50, so I can find RO1. VA over IC, and I can use this formula when I neglect VA in the DC analysis only. So 50 over 1, 50K. What else do I need? RE is 12. I know RE is 12. No, excuse me, 0.6. And I still need R pi 2. R pi 2 would be the same as R pi 1 because they're biased at the same IC. So, and they have the same beta. All right, so, and now we can find the input resistance, 2.5 plus 101 times 50 parallel 0.6K parallel 2.5K. And we should get 50.9K. And that's the input resistance in this case.